Pure metals have a single freezing plateau temperature. They have that horizontal freezing temperature. Now, alloys, two or more metals, do not have a distinct freezing plateau temperature. They solidify over a temperature range. So you can see that here we have an alloy of two or more metals, and the freeze in the latent heat line is no longer horizontal. It is a freezing range. The freezing temperature is much, much higher than the freezing finish temperature. So alloys have a freezing start temperature and a much lower freezing finish or solidification temperature. So alloys display a freezing range of temperature. Now, during the freezing range, the temperature will be cooling, falling to the freezing finish temperature. So we have a freezing temperature range. And when you come to the end of the freezing temperature, the solidification temperature, the solid alloy will then cool to room temperature. Now, it's important to understand that in the freezing range, the solidifying metal will consist of slush, an icy slush mixture of solid and liquid. So in the freezing temperature, the range between the freezing start temperature and the freezing finish temperature of an alloy, that in that area, the freezing metal is a mixture. It's a mixture of solid and alloy. It's a slurry of solid islands in liquid. That is very important because it has implications for welding. At the end of the freezing temperature, again, when we've lost all the latent heat, then the alloy will be all solid and the solidified aluminium cools down to room temperature. So let's have a look at how structures develop. In the liquid state, we've broken down the metallic bond. So at high temperature, we've broken down the metallic bond, and we've got a soup of atoms loosely held together by cohesive forces. As the liquid solidifies to the freezing start temperatures, atoms come together to start forming the single-faced centered cubic, the basic building block of aluminium. Now, at this point, throughout the freezing liquid, many thousands of face-centered cubes will randomly form. So at the start of the freezing temperature, aluminium atoms come together, and initially they form the face-centered cubic, and millions and thousands of these cubes will start forming throughout the liquid stage. Now remember, each single cube will grow three-dimensionally, and the 5 atoms of all 5 faces of each cube will be shared with and or form adjacent cubes. The adjacent sharing of the 6 faces will be replicated many thousands of times across the adjacent cubes, growing into crystal lattices. So throughout the cooling temperature, the face-centered cubes will start growing adjacent cubes and in 3 dimensions, and they will grow into crystals. Thus, many thousands of crystals will grow randomly across the freezing liquid. Now we need to understand a little bit about how alloys freeze, how they solidify. Now remember, no two pure metals have the same freezing temperature. And when we alloy two metals together, they would develop a freezing range which has a different freezing start temperature. So on our graph, we on the left-hand side, we have 100% pure A metal, aluminium. On the left-hand side, we have 100% pure solvent metal. And note that they have a single freezing temperature. They are pure metals. As soon as we put the two together, mix the two together, we've lost the single freezing temperature. Now we have a freezing range. So when we alloy two metals together, whether it is metal B in A or metal A in B, we've now developed a freezing range, and you can see that we've lost a single temperature. And if you look on the left-hand side, 80% A and 20% B now has a very, very long freezing temp range. And that freezing range will be a basis of the analysis, the concentration, the solute in the solvent atoms. Now, importantly to understand, and you can see that irrespective of the different analytical combinations, whether it is 80% A, 20% B, or 20% A and 80% B, the finish temperature, the end of the finish of the cooling curve, the cooling range, is a constant temperature, which is exactly the same across the entire analysis. And that constant finishing freeze temperature will be lower than the freezing temperature of either of the solvent or solute metals. Now that means that the resultant alloys will solidify at a constant temperature much lower than either of the parent metals. So we've completed the graph now, and you can see the pure metals have a single freezing temperature. As soon as we create an alloy, 80% A, 20% B, 60% A, 40% B, we have a freezing range. And the freezing finishes at a constant solidification temperature, irrespective of analysis. And that freezing temperature is much, much lower and will be much lower than either of the freezing temperatures of either of the pure metals. Depending on their analysis, and that's the analysis composition of the solute solvent metals, whether it's 20% A, 20% B, or 20% A and 80% B, the alloys will display a freezing range. And depending on the analysis, that freezing range can be very large. So if you look at 80% A, 20% B, down to the solidification temperature, that is a very long freezing range. If we go to 60% A and 40% B, the freezing range reduces. Now remember, in the freezing range, it's mushy. It'll be solid islands of solidifying aluminium within liquid. And that long freezing range is important when we are welding aluminium, when we're casting aluminium, because it means that we will have a long area or a long time where the aluminium is semi-liquid, semi-solid, and mushy like ice in water. Now, alloys are not pure metals. So alloys, because they are mixed with another metal, can never be 100% pure aluminium. So the freezing start temperature of an alloy will be much lower than that of aluminium. Pure aluminium has a melting temperature of 660 degrees C. But as soon as we alloy it, because we have no longer got a starting temperature of pure aluminium, the melting temperature, the solidification temperature of any alloy will be lower than that of pure aluminium. So the freezing start temperatures will be much, much lower than that of pure aluminium. Now we need to construct a diagram. We've seen diagram A and B, but we now need to construct a eutectic diagram. And we're going to construct a eutectic diagram for an alloy of two metals A and B as we've done. Now, eutectic is the Greek word meaning easy melting. The freezing start temperature lines. Now, these are the lines that separate pure liquid from solidifying metal. So the line that separates pure liquid metal from the mushy metal where it is starting to freeze, we term those lines liquidus. And the slope of those lines are a function of the alloy composition. Above the liquidus temperature, the alloys are all liquid. Below the liquidus temperature, freezing has started, so the alloys are a mixture of mushy. The freezing finish temperatures we call solidus, and below these temperatures, the alloys are all solid. Now, I need to introduce a concept. If you look on the extreme left-hand side and the extreme right-hand side, you see that there is a triangle. And that the solidus lines, if you look on the left-hand side, you can see that the solidus line slopes down to the solidification line in a particularly, in a downward slope. So we have a solidus line that the alloy finish temperature is horizontal, but on the right hand side and left hand side, you can see the lines sloping at an angle. These are the solidification lines. And on those areas, you can see that the solidifications change massively for small increases in analysis. Once the metal is solid, we have two other concepts. And you can see on the left-hand side, I've marked a line solvus. And solvus is a solid solution line, which we shall explain further on. And in the middle, we have a eutectic temperature. You will notice that the eutectic temperature is a constant temperature again, and much, much lower than either of the starting alloys. Hence the term easy melting. Now, all alloys, irrespective of their analysis or analytical composition, exhibit across their entire analysis a constant freezing finish temperature, which is when they will be all solid. We term this constant freezing temperature line the eutectic temperature line. In all alloys, there is a composition point, a function of these alloys, where again the freezing temperature and the freezing temperature, finish temperatures are identical. We term this temperature the eutectic temperature. Note that the eutectic temperature is much lower than the freezing temperature of either of the parent metals, hence the term